Alright, I'm just pulling things up and then we'll begin. And then I think I have Sea Lion pulled up, right? Yep. Oh yeah, if you remember from last lecture, I actually had, let's see here. Here we go. If you remember, I actually ran this quadratic. Which quadratic sort was it? I think it's insertion sort. Yeah, I ran insertion sort on 1 million randomized elements, and it actually finished. I let it finish. It took, well, how much did it take? 60 times. And it took about 1.88 hours to finish. So that would be longer than a single lecture. So basically the point is that, if you have a quadratic sort, you're not very, make sure that you stay with numbers that are relatively small, say, under 1,000 or under 10,000. Otherwise it can start to get pretty bad. Okay, so today I wanted to talk about, basically, I've been talking about Big O, and maybe we'll do a little bit more of the mathematics of Big O, rather than the algorithmics of Big O, and we're also going to talk about Big Theta and Big Omega. And so that's what I plan to do, and then we'll start on binary search trees, maybe. Just have to remember how to click on things. Let's see. Extensions, render, mathematics, LaTeX. Okay. So. Alright. So basically, remember the definition of Big O. The definition is basically this, right? We would say that f of n is equal to O of g of n, when, let me just do something like this. Always takes a long time the first time you render. So this is the notation we generally use. And so what does it mean? Basically what it means, there is an n, really, like, let's just call it capital N, and a constant c, so that, and let's write a little formula. F of n is less than or equal to c times g of n, right? So you get to stick the constant on g, where'd it go? There it was. So this is the formula that we're looking for. And then the last thing to say is whenever n is bigger than or equal to, or I should say little n is bigger than or equal to the starting n, right? The starting capital N. So basically the way to say this in English, or whatever, is that f of n is smaller than some constant times g of n after a certain point, and then forever after that. So at some point, so there has to be some constant that you pick, and what's going to happen is that f of n is going to, it's going to be smaller than, technically, or equal to g of n after some point. So that's, and you can change the constant. So for instance, if I asked you, is, say, 3n squared plus 2n, 2n plus 1, is that equal to O of n squared, right? Let's go through the actual argument to show that that is the case. That's the only thing I don't like about this math rendering thing. It always sticks it off screen. But what are you going to do? So is this true? And the answer is, I think so. let's see. Do I have the chat minimized? Or oh, I had the chat like turned off or something. Sorry about that. Or maybe I didn't. I don't know. So you wanted to be reminded how to submit code via GitHub? Sure. So let's pull up the Discord for a second. Hopefully it's in, yeah, there it goes. Let's go to my section of 341 and let's go to announcements. Okay. So basically what you're going to do is you're going to go to this link here. Let's pull up a window. And then what you're going to do, so it already kind of knows me, but what it's going to show you is it's going to show you a username. Once you have to make sure that you register your email. So you'll do it. You'll give it an email, and then you'll get registered, and then you'll click on your homework 1, and then here there should be an add file, and you can just click upload files, and that's it. Just upload whatever files you want to upload. So homework 2 is going to be mostly math, so we won't have any coding there, but I kind of wanted to get people at least onto the GitHub. That was the whole point of. That's kind of the whole point of doing it. Maybe in the future, what we'll do is we'll have we'll actually use GitHub for the PDF submissions of everything, because you can add all kinds of files. You don't just have to add code files. You can add text files. You can add anything. So, yep. So that's how you do it. You just add the file, upload, and then select your files. Yeah, so if all you see is go-to file, then I don't think you're fully registered. You have to verify your email address. So yeah, if you haven't verified your email address, someone else helped me figure this out, because of course I'm using this is like my personal account, right? My other GitHub account. But the point is that I had registered that account, 10,000 years ago. So I didn't realize that if you don't verify your email, exactly. If you don't verify your email, then it will not let you add the file. And I honestly didn't know that. I wish that it would say something, but GitHub is not always the most helpful in terms of its verbosity. Sometimes it's just a little bit scant on the details. But at least you're going to get some practice with GitHub, because, I mean, this is like real professional coding practice, right? Okay. So that's all that you really have to do to submit your assignment. There's also a GitHub desktop that you can do if you want. So you can always download GitHub desktop and then use the link here to submit to that repository. It takes a little bit of figuring out. It's not 100% obvious how to do it, and I don't really want to teach it because unfortunately it's kind of annoying. But once you figure it out, then it's actually really easy to submit stuff in the future. But again, that's up to you. You can use GitHub desktop, you can kind of learn it, or you can say screw it and just drag and drop files and that kind of thing. So, yep, so that's how you submit. And I know that it's annoying to do 2 submissions, so probably for the next assignment we'll probably just do it on, I don't know, I'll think about it. Maybe we'll just do it on GitHub. But there won't be any, I don't think there's going to be any coding in the next assignment. Okay, so let's go back to the Big O analysis, because, this is like obviously the most fun thing that you've ever had to do in your life. So, if you turn it in, this time turn in the PDF on Blackboard. So, PDF to Blackboard, code to GitHub this time. Next time, maybe, anyway, we'll figure it out for next time, but I think it's, the Blackboard submission system on my end is a little bit annoying, so maybe GitHub is just as good on my end, so maybe, yeah, I'll think about it. I think maybe we'll switch to GitHub full time, even for non-code. Anyway, okay, so, is it true that 3n squared plus 2n plus 1 is big O of n squared. And so we basically have to think about what this means. And so the question is, right, 3n squared plus 2n plus 1 going to be less than or equal to, right, some constant times n squared eventually. Let's see, does f of n equals n squared? That's a good question. We'll get to that once I'm finished with this problem. But that is the next problem. Yes. So is it true that this is true? And the answer is yep, because n is less than n squared. Constants are less than n squared. And we can set c equal to 6, right? So what we can do is we can set c equal to 6, and then if you agree that, you know, if we just change these all to n squareds, instead of being 1, we change this to 1n squared, we change this to, basically this is what I'm saying. This is the kind of mathematician's way to do it, which I think is actually pretty, you know, cutesy, and it gets the job done, is really the point, is that it takes care of all the stuff you need, and it's a pretty easy way to bound these things without having to work too hard or think too hard about it. So what you do is you just say, okay, if you agree, and I think we can take this, we're a computer science class, so you don't have to prove that n is less than n squared for at least n bigger than 0, but even for n less than 0, it's still true. It's only not true between 0 and 1, right, in that little region. But those are for non-integer n's. So actually, because we're doing integer n's, we're saved from even the exception of the little polynomial business that can happen. So if we look at this thing and we say 3n squared plus 2n plus 1 is less than 3n squared plus 2n squared plus n squared, which is true, is equal to 6n squared. So the answer in overall is yes. We pick c equal to 6. Big N, we can even set it to equal to 0 or 1, whatever you want. And therefore it's true that 3n squared plus 2n plus 1 is big O of n squared. Okay, so that's a decent example. So now let's talk about the example that was brought up just there. So let's say that you have, let's ask the same question, but now let's ask if 3n squared plus 2n plus 1 is big O of n cubed, right? And you would say, well, is it big O of n cubed? Hard to say, let's think, right? So the question is this thing true? Right, so here's example 2, I guess. So I'll label this as example 1. I'll release, I usually release these PDFs, so this is example 1. And so, is this true? This was true. Is this true? And the answer is also going to be yes. And the reason why is because you know that, 3n squared plus 2n plus 1 actually is less than or equal to 6n squared. But then you know that, separately you know that n squared is less than n cubed, right? Because basically, in order to prove that, all you have to do is here's the argument. I mean, you don't actually have to provide this argument, but you would basically say that I know that 1 is less than or equal to n, right? I know this as a fact. So, at least when you pick, as long as you pick your constant, capital N is equal to 1, right? So if you pick the constant there, then what you can do is you can multiply both sides of this inequality, sides by n, and so that what you're going to get there is then you'll get 1 is less than or equal to n is less than or equal to n squared, but then you can also do that one more time, right? If you multiply all the sides by n again, then what you're going to get is that 1 is less than or equal to n is less than or equal to n squared is less than or equal to n cubed. and then that should satisfy you, right? Hopefully, theoretically. So, do we assume that n is natural? Yes. And the reason why we assume that n is a natural number, so we assume n is a natural number because n represents, right? What does it represent? It represents like a number of data elements that we insert or we feed into our algorithm, whatever our algorithm is. And so let me just use the set notation because I like the set notation. And so we assume that n is a natural number because these n's represent natural numbers, right? So we assume that n is an element of the natural numbers because they represent, they always represent the number of data elements. So if something isn't true for like fractional values, or if something doesn't exist for fractional values, it's okay because n should never be a fractional value, hopefully. Maybe you have an algorithm that takes a fractional sized input, but I've actually never seen anything talked about that way. Normally we always talk about it as a discrete thing in the natural numbers. So, okay. So here the answer is that since n squared is less than n cubed, we can pick the constant c is equal to 6 again, right? 6, n is equal to 0, or n is equal to 1, or whatever, right? So you can pick n is equal to 0 or 1, and what this does here is this choice of constants means that this is also true, right? Yeah. As I was saying, I kind of explained that in words. I didn't write it down, but as I said, there is that little exception, right? Let's see if I can find it. Here's Desmos, right? So what you're talking about is the fact that if we let f of n equal to n, and you say g of n is equal to, say, n squared, and you see, technically, g of n, the n squared, is not always bigger than f of n, but look at where it happens, right? It happens between 0 and 1, and it's only true for the fractional values in here, right? The good news is that's also the reason that we include that constant n, that capital N constant, because what it allows us to do is if you're even vaguely afraid of something like this happening, then what you do is you say, just start it at n is equal to 2, right? And after this, it's never going to be a problem, right? No one really cares how your algorithm performs on 0 elements or 1 element, right? That's not the purpose of Big O. The purpose of Big O is to ask the question, how does my algorithm perform on 100 elements, 1,000 elements, 1,000,000 elements, 1,000,000,000 elements, right? How does the performance change when I go up asymptotically? If you're talking about the performance of an algorithm down here where, 0 is, hopefully your algorithm doesn't take too long on 0 input. It doesn't really have a value in here because these are all fractions, and then hopefully it performs pretty well on a single input. If it doesn't perform well on a single input, Big O doesn't really capture that because you can always set the constant n to 2 or 3 or 4, and you can just escape the initial stuff. But yeah, so when I say that it's true, that this is true, right? Basically what we're assuming is that you start n at 1, and so here, maybe if you're feeling really safe, you could just start n at 1, and that way it will never ever possibly be a problem. Yeah, so, okay. Cool. So let's look at another example. So here's a question. Is n squared O of n log n? And I'll just use regular log, even though it doesn't matter. So, and I'll explain why it doesn't matter in just a little bit, but yes. So, is this the case? So actually, maybe I wonder if there's a way to fix that problem. So here's example 3. And so the answer here is actually going to be Russian. Let's try again. No. So, okay, so, God. So, right, so the answer, the hint is that it's no, but then the question is why? And so the argument goes basically like this, right? Let's assume, so this is a proof by contradiction, right? So this is basically like Math 203 again. And so the answer here is we assume that it is big O. And so what we do is we say, therefore, there is some constant c, some value n, so that, right, so that n squared is less than or equal to c times n log n. Okay. And of course the value is stuck out into the abyss again. Here we go. So basically this is what Big O is saying. Big O is saying we're going to assume that there is some constant c that does this. So then what we're going to do is, I don't know, say, now it's algebra time, right? So what do we do with algebra? What we do is we divide by n. I feel pretty safe dividing by n. Remember that n is always going to be bigger than 0. If you remember the rule, if you divide by a negative, you have to flip the sign of an inequality. But I'm not going to do that because guess what? As it turns out, we're always thinking positively here, always optimistic, right? And the reason why we're always thinking positively is because I don't know what it means to feed a negative number of things into an algorithm, right? So the good news is we can always pretend that n has to be positive. Okay, so now we're asserting this fact, and this fact is actually definitely false. And we can do it experimentally, or we can do it, you know, algorithmically or whatever. So if you think about it, there's an issue here, right? If we're asserting that n is always less than or equal to c times the log of n, now the question is, how do we prove that this is false, right? Because it's the exact opposite, which is true. Yeah, you can actually do that. So that's one of the ways to do it. That's definitely one of the ways to do it. So, yeah, so what you can do is you can say divide by n again. And I'm basically doing what you said. I'm doing a slight modification of what you said, but whatever. And so here we're going to have log n divided by n. Right, and so what we're going to do is we're going to take the limit as this goes to infinity. Right, so we're basically going to take the limit as n goes to infinity, and we're going to take this limit as n goes to infinity, and we're going to see what happens. So, come on, why are you stuck on all the way there? So, I'm not going to ask you to do this ever again. This is not really part of algorithms or Big O or anything. This is just the fact that, like, this is the actual kind of proof for what's going on here. Now, of course, you would say, aha, n over log n, or log n over n, or whatever. This is an infinity over infinity, right? So this is in indeterminate form. So, well, calculus is basically just algebra plus plus, right? So, anyway, the point is you don't really have to do this on paper most of the time, but yeah, exactly. So you would use L'Hopital's rule in this case. So the derivative of log n is something. Who cares? It's actually 1 over, what is it, like 1 over the natural log of 2 times the 1 over n, or something like that. Again, who cares? We're going to absorb that. We're going to forget about that log. I mean, I might write it out, but you don't have to worry about it because it's just a constant. So we're going to get c over the natural log of 2. And so the derivative of 1 is, or derivative of n is 1. The derivative of log n is going to be 1 over n, basically. Right? So here we're going to have times 1 over n, and that's still in the limit, right? The limit as n goes to infinity. N goes to infinity. And so basically what we're going to say, and so we're almost there, and then we can stop doing calculus. What I'm going to say is that we know something about 1 over n, right? We know something about 1 over n as it goes to infinity. 1 over infinity is equal to 0, right? So there's a slight problem here, right? Because I'm claiming that this is true, and therefore 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 this would be true, and therefore, right, and therefore this would be true. Now, of course, you say, well, 1 here, oh, this should be less than or equal to. Let's actually just draw that line in, because I'm lazy. There we go. So, yeah, but we're not using log, we're using, well, okay, we're using, actually, I used it in, you know, kind of, yeah, we're not doing log base 10, we're doing log base 2 in general, but I guess it's, sure, you could do log base 10 and then have that, right? I'm writing LG, which is log base 2. It really doesn't matter. The whole point is, like, who cares, right, about this constant? Nobody. And you know why? Because, the problem is that this constant's going to get insta-killed by this 1 over n, which turns it into 0, right? So you can change it to log base 10, which is unfortunately what I wrote up here. I should have just stuck with log base 2. But yeah, you know, here's LG. I've used LG most of the places, so let's just stick with LG. So yeah, the constant dies instantly, so it doesn't really matter. So there you go. So this is a contradiction, right? Because as it turns out, 1 is not less than 0. And that's really all you need. And so now what we know is that the only thing we did, the only actual assumption we made, right? Everything here was just calculus, then algebra, 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 algebra. So the only assumption we ever made was that specifically that was that n squared is O of n log n. So this can't be right. The end. Right, so this is kind of how you would show. Honestly, let's just admit that from now on you are allowed to assume that log base anything. So let's make it even more general. The log base a of x is, or log base a of n is less than or equal to n, as long as, I guess, what, a is bigger than 0 or something, or a is bigger than 1, right? Technically you could have negative exponents or something like that, but you're allowed to assume this from now on, as long as a is for some n, or, you know, for all n bigger than some starting n, and for a bigger than 1, technically, but I promise you I'm not going to mess around with fractional, well, I hope I don't ever mess around with fractional log bases, or, you know, decimal log bases or something stupid like that. So, yep, generally log base A. So in this case, where really if for all intents and purposes A is equal to either 2, E, or 10, right? So those are the ones that we really care about. And so this is true, and so you can basically use this in the future if I ever ask you to do big O proofs or anything like that. So let's actually prove now that, what's another thing to prove? Like e to the n is big O of, say, n factorial, or, well, let's not do that one. Well, okay, let's do that one. So O of n factorial. So let's do another example. I think this is what, like example 4. So is it true that 2 to the n is big O? Let's... Yeah, I mean, so it would actually be easier to do it with E than that because of Stirling's formula. Anyway, well, actually, you know, it's not. So we can do it in a much stupider way, and so I'm gonna do it in that stupid way. Just watch me. So I want to show that 2 to the n is less than or equal to c times n factorial. And so, of course, let's all remind ourselves what all these things are, right? So basically, 2 to the n is equal to 2 times 2 times 2 times dot 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 times 2. And how many times is that? It's n times. So let's write that out. Let's say, actually, let's do it in LaTeX. So we can do under brace, and then we can do n times. And we want to show that that's less than or equal to n times n minus 1 times n minus 2 times all the way down to, say, 3 times 2 times 1. And let's see here. So 2c dot. Let's just do a copy paste a few times, and then some dots, and then 2 like that. So let's see what renders out, right? This could be great, or it could be the worst thing that you've ever seen. Oh, look at that. It actually rendered correctly. Ah, wonderful. Wonderful. So, oh, I forgot the constant c. There we go. There it is. So c is stuck on the end now. Okay, so how do we run this proof? So here's the stupid way, which I think is a good way. What I'm going to do here is I'm just going to say, well, do you agree that 2 is less than or equal to 2? Right, so I'm pairing... I'm pairing here, and then I'm going to pair this with 3, and then I'm going to say, and then I'm going to keep going all the way up to crap, come on, just draw me a nice little, there we go. And then say this 2 that's hidden here, we're going to compare it with n minus 1, and then the other 2 that's also hidden here, we're going to compare it with n minus 2, etc. So here's the way to really think about it. So is 2 less than or equal to 2? Yes. Is 3 less than or equal to 2? Or I'm sorry, is 2 less than or equal to 3? Yes. Is 2 less than or equal to 4? Yes. Is 2 less than or equal to, say, n minus 2 or n minus 3? Yes. Is 2 less than or equal to n minus 1? Yes. Well, as long as n is sufficiently big. Of course, you can always say, as long as n is bigger than, say, 5 or something. Let's make n bigger than 5 just so that we know that n minus 2, it's always true, right? Otherwise, You could say, well, n minus 2, if n is equal to 1, then it could be 0. Who cares, right? We're not talking about low degree small n's. We're talking about big n's, right? This is big O, not small o. There's actually a little o, but we're not going to talk about it this semester because it's really confusing. And so then the last question is also yes, right? So this is one way to do it, and you basically say, okay, at this point, what I get to do, now I'm just going to say, okay, multiply all of them. And so what we see is that the only time where it's not true, there is one exception. And that's with the first term, right? The first term, where we have 1 here, is not less than 2, right? So our problem is, in fact, that 2 is, this is false. So, issue, right? But the good news is that we have the constants, we can change c equal to 2, right? So instead of comparing it against this original 1 here, so here's this 1 that, let's see, no fill, there we go. There's this original 1 here, which could cause us some issues, right? Because it's not actually bigger, right? So that's a problem. But the good news is that if you just draw your circle a little bit bigger, then you're okay, right? So instead of comparing one of these 2's against 1, and then that would be false, you compare one of the 2's against 1 times c, and remember, you get to choose c at least once during the problem, so you get to choose c, so we can set c equal to 2, and that makes us happy because now we're back to 2 is less than or equal to 1 times c, which is equal to 1 times 2, which is good, right? So this is one way to do it, and I think it's a pretty decent way of showing that. So if you ask, like, are there any algorithms that run with factorial time? So if any of you have taken linear algebra, the determinant algorithm of a matrix runs in O of n factorial time. If you use cofactor expansion, there's a way to make it go much faster. But if you only use cofactor, if you use row reduction and then multiply the diagonal elements, then you'll get the determinant again, and that's in quadratic or quartic time or something like that. Yeah, exactly. So that's why you would right? So here I set n equals to 5, and so that's a pretty good n. Right? As long as you set it sufficiently large that it misses any of that early stuff that you really don't want to care about, right? So if there's bad behavior in the early parts of the function, you definitely should set n larger just so that it misses all of that stuff. Is it true? Let's look at it. Let's see, 2n factorial. Huh, it actually graphed it. And then, let's see, 2 to the n. Let's see what happens. Oops, come on. I think instead of doing, yeah. So it's actually not graphing n factorial precisely here. There we go. Yeah, it's using the gamma function to do it. As it turns out, in this range here, well, so actually it's equal here, and then it's good for the rest of it. So actually, it's correct that 2n factorial is bigger, even on this range, right? So technically, 2x factorial doesn't exist on 1, 2, right? You would have to, if we were being absolutely mega technical, we'd say, you know, it'd be like 2 gamma of x. But again, like so this is really one of the reasons why we restrict ourselves to natural numbers, and we restrict ourselves to, you know, and not worrying about the gamma function. So, you know, what's the gamma function? I don't even know. It's crazy. Totally crazy. Why would there be a function that's named gamma? There's no alpha function or beta function. Actually, there are functions like those, but whatever. So, anyway, so there are things that actually run in O of n factorial time. There's other things that run in exponential time. A lot of graph searches. Or, I shouldn't say graph searches, because graph searches can... well, anyway. So, I don't want to say too much about that, but certain graph algorithms can run exponentially, i.e. traveling salesmen and stuff. So there's a bunch of stuff that you don't have to worry about, but this is a good way to do it. Okay, so I think that's pretty decent. Okay, so those are some pretty good examples of how various big O stuff works. So the last thing I want to talk about is big theta and big omega. So let's talk about big omega first. So big omega is basically the same as big O, except it's reversed. And what do I mean by that? I mean literally that, let's look up the definition. So let's just copy paste the definition. So this is all big O stuff, so let's replace it with big omega. Okay. Let's say that f of n is big omega of g of n, right? The good news is that we are not being as technical as mathematicians here, okay? So there's a lot of things that we just kind of glide over. And of course you would say, here is the big O equation. And so for the big omega equation, here it is. Right, so here it is once it renders. Are you going to render? There you are. Good, 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 good. Okay. So all we need is we flip the inequality, right? That's all we do. And so big omega, right, where this is the capital omega, we say that f of n is, and so we read this equal sign as is. You see this equal sign in a lot of books. You see is in a lot of books. I actually prefer something a little bit more mathematical and a little bit more, I'll say, correct, where instead of saying f of n is equal to big O or f of n is big O, I prefer to say, or big omega, I prefer actually to say that f of n is in, using the set notation, omega of g of n. And the reason why I prefer to use this set notation rather than anything else, and I may actually start using the set notation, I don't know. I might use the equals, I might use is. The problem is that textbooks are very inconsistent on this issue, and I actually don't see many textbooks choosing my answer. If you notice, this is the set inclusion symbol. So basically, this is a set of functions, and this is one function in the set. Right, so that's how I prefer to think of it. The reason why I prefer to think of it this way is because then it actually makes sense. And you can arrive at some bad conclusions if you use this as a direct equal sign. Because if you say that f of n is omega of g of n, and g of n is equals omega of h of n, and then like, is f of n equal to omega of h of n, it's like, what does the equal sign mean, right? Yeah, exactly. So the set inclusion symbol should also be used for big O, really. So if you use it for big O, that's also, I think it's more correct. I know that it's silly to really harp on notation, but I think the thing is that I think it's the most correct. Oops. So I guess I accidentally. Oh no, wait, no, I didn't. Oh yes, I did. I did something bad. That's the like Nordic O sign or something like that. So I actually prefer this notation, and the reason why I prefer that notation is just because it makes this into some kind of object, and this makes it this is a set, and this is one of the objects inside of the set. And if you do this, it's actually there's no way to run into mathematical problems. Whereas if you use the equal sign, there are tricky ways that you can end up in mathematical danger, where you end up with something that's false. The problem is, and the reason why I still write this down sometimes, is because even though it's dangerous and an abuse of notation, you will see it in books, websites, etc. So it's definitely abusing the notation to the point of danger. But yeah, so that's as much as I always say this, and I don't know if anyone actually cares about my notational hang-ups. But anyway, yeah, I just have this notational hang-up because I believe that it's better to think of it as like this big O of thing as a set of functions. It's like a family of functions rather than being some nebulous object. Okay, so let's talk about big omega a little bit. So big omega just says that we can multiply by a constant c and get it to be a lower bound, right? So what this means is that f of n is greater than some constant times g of n at a certain point, and then forever after. So that's all we had to change here. So a lot of times we'll use big omega for lower bounds of runtime, and a lower bound of a runtime is often the best case of the runtime. So if we say that, for instance, say quicksort performs, let's just say quicksort performs with a best case of omega of what, n log n, and a worst case of O of n squared. And the reason why you would say this is because you say big O is the best case. Big O is the worst case. Big omega is the best case. And the reason why you would say that is because this says it can be no lower than g of n, right? And this means it can be no higher than g of n. So what it means is the worst case is no worse than that, right? So the worst case is no worse than basically c times g of n. And here the best case is no better than g of n, right? And so that's the way to think about it. And I guess you could also put a c onto that too. Okay, so, basically, yeah, that's kind of what it means. What it means is that, like, if you have something, that's kind of what it means, right? So a lot of times, and here's the thing, I don't really care about if you're very careful with that, because I think if I say what's the best case and you say O of n log n, I don't. What I assume is that you mean that the best case is, you know, some constant times n log n. I don't assume that you mean that it could theoretically, even though constant time is in O of n log n, right? I don't assume that you mean that, right? And all of this gets into, even here, so let me just say that this is what a lot of people do. I don't actually really care if you use Big Omega as best case or worst case, but that's definitely what some people do, because Big Omega is like the opposite of Big O. So for example, and it kind of gets a little bit confusing. For instance, you can say something like n to the fifth is basically is Big Omega of n cubed, right? Something like this. And this is true, right? And the reason why this is true is because we know that n to the fifth is just greater than or equal to n cubed after a certain point, right? And that's true forever. So it's weird because you're looking at a function that's a higher degree outside than the function inside. But remember that omega flips our intuition on our head a little bit. So omega, so the way I like to think about it is that, or I don't know if this helps or anything, O can stand for overestimate, right? Omega is this symbol here, so when you have this omega symbol here, you notice that it has lines under it. So the way I like to think about that is that omega is the underestimate because it has the lines under it. So I guess that's generally how I think about it. So this line is saying underestimate. And then there's one last thing that we haven't talked about, and that is big theta. So now let's define big theta. So capital theta is this symbol here. And it's even better because if you look at big theta, it kind of shows you graphically what it means. So O is like an overestimate, omega is like the underestimate, and then theta looks like it's going right through the middle. And what mathematicians tend to call this is what's called a tight bound. And what I mean by a tight bound is this. There are two constants now. Let's say that f of n is in theta of g of n. So if f of n is in theta of g of n, then there are two constants. Let's call them, I don't know, c and d, or maybe a and b, or whatever. Right? So this is what we're claiming. F of n is in theta of g of n. Then there's two constants. Let's call them a and b for now. You can call them whatever you like, right? You can rename the constants whatever you like, but who cares? A times g of n is less than or equal to f of n is less than or equal to b times g of n, like this. So what this means is that there's one constant where you can go under, and there's another constant where you go over, right? And so, for instance, if I claim that, say, 3n, let's just use this, 3n squared plus 2n example is basically theta of n squared. So I'm claiming this now. So there's two constants so that this is true. So that this is true after n is bigger than or equal to, so some starting n. Right, so this is what, whoa. So, let's see, did I screw it up? Okay. So I claim this is true. So let's do crap. Didn't render. Let's try again. Because I want it to render. That is not a parenthesis. Okay, there we go. Sometimes it literally just doesn't render the correct LaTeX. Like, I don't even retype the LaTeX. It just doesn't re-render. Okay, so I want to claim that this is true. So what I'm going to do is first I'm going to say, well, I know that 3n squared plus 2n is going to be bigger than n. So I know that n squared itself, right, just with a constant, say a is equal to 1, right, and I know this is a little bit of an abusive notation, but I think you understand what I'm doing, is less than or equal to 3n squared plus 2n, which is less than or equal to, say, 5n squared, right? And then I'll set that 5 equal to b. Something like, ooh, I did a naughty thing. What did I do? That's what I did. Didn't put a space. I continued to do a naughty thing. I gotta find the error in my LaTeX code. Oh god, I still did the same naughty thing. Okay, there we are. Okay, good. Alright, now we got it. Unless I do something really dumb like rotate the entire picture. And then of course it doesn't render correctly. Come on, let's try. Try a little harder. Get me... There we go. Hopefully this rendered correctly and didn't do some crazy symbol. It looks right. And I know, of course, you can say that there's an abusive notation here where... I can't tell if it's straight or not. Okay, there it is. More or less. Hopefully no one's seasick. Anyway. So basically, if you choose a constant a such that it's lower, and then here's your function f of n in the middle, right? F of n in the middle. This constant a makes us less, and then the constant b makes us greater. And so you notice that basically, and let's actually draw this out. So if you have f of n equals to 3n squared, come on, squared plus 2n, and g of n is going to be equal to 5n squared, and then we have, say, h of n is equal to n squared, which I will then draw here. So what we're going to see here is that it's true that in the beginning part, our f of n is actually bigger than one of them, but remember, we get to set n, so we'll set n to be, say, 3, and then after n equals 3, which is somewhere early here, what we see is that, actually what we should do here is, what is it? We should adjust the x-axis stuff. We should say that we go from 0 to, say, 5, like this. That makes it look a little bit better, doesn't it? So if we zoom out here, what we see is that, yes, it's true that actually this function was bigger early on, right? Less than 2. But after 2, what we see is that the asymptotic behavior takes over, right? 5n squared is bigger than 3n squared plus 2n, which is also bigger than n squared. And so that's what the good news about big theta gives us, is big theta gives us, this is what's called a tight bound, right? Because if you have this tight bound, then the thing is that it doesn't matter as long as the function stays, the red function stays between the blue and the green function, right? Because the blue function's the overestimate, the green function's the underestimate, and you see that they're both, these two functions are both actually quadratic functions. So we get to basically just say that 3n squared plus 2n is theta of n squared. So that's what we get to say. So if we look at something that's a little bit weirder, right, we could always introduce, for instance, like some kind of sine component to it, even though, you know, you'd be hard-pressed to... I doubt that you'll find a lot of algorithms. There are some, but there's not many algorithms that run in O of sine of theta or O of sine of n time. But you see here that even though we've introduced this like weird squiggling, right, to the algorithm, or maybe we even introduce, say, plus 5 cosine of n squared, right? Or I think you can actually put the squared here to make it more classical, right? There you go. So you see here that we've introduced all kinds of bizarre squiggling to this algorithm, right? And maybe even make it n log n, log n, something like this. So we can make this algorithm squiggle really badly, right? By adding some weird kind of sinusoidal, cosine terms, log terms, all kinds of weird stuff. But what do you know? What do you see that's happened, right? Has anything actually changed about the asymptotic performance of that algorithm? Not really, because the 3n squared is the dominant term here, right? And because the 3n squared is the dominant term, it doesn't, all these little local squiggles up and down, right? Like, this would be a weird algorithm that actually performed better here, and, you know, weird, right? But who cares, right? The whole point is not that there's an algorithm that actually has this runtime. The point is that if an algorithm had this runtime, you could still say, as weird as this runtime is, you could still say that it had theta of n squared performance, right? And so this is where all of the real world stuff gets introduced, is that a lot of algorithms will have a lot of like little local issues that like this that will happen, but overall you can say that it's theta. And so yeah, so basically if something is theta of another function, so if f is theta of g, right, f is theta of g, and I'll put a big theta there, means that g is also theta of f, and maybe I'll have you prove that on a homework. The hint is that you can, well, the hint is use the a's and b's, right? Use a's and b's. That's a good one. That's a good homework problem, right there. The other thing is that if f is theta of g, then f is big O of g, and f is omega of g. Okay, so those are the other true statements. Is that and is this an if and only if? Yes. IF, which if and only if, which means that if f is theta of g, then f is O of g and f is omega of g. That's pretty easy to prove, because if f is theta of g, then we have the omega formula here, right? This is already the omega formula right here with a constant a, and we already have the constant b formula with the upper bound, right? So that's how you would prove it. You would basically say the proof of this is that f is theta, assume f is theta of g. And I know I'm not using the theta notation, but right now I'm too lazy to do that. So I don't want to be putting thetas in there. I guess I could just like keep a theta. I think there is a theta that I just made. We could just copy paste it, so I don't have to keep recompiling the LaTeX. So assume that f is, right, and let's put some spaces in there, theta of g. Wonderful. Then what you say is, therefore, there exist constants a and b, so that the formula that I wrote down is true, so that this is true, right? So there exist constants a and b. Oops. See, that's the problem here. Got to stick this back here. So given that there exist constants a and b such that this is true, and you can even say for n bigger than n, or n bigger than or equal to n, something like that. Then what you do is you say therefore, or thus, or consequently, or whatever, f is omega of g because of this part of the expression. So because of this right here, right? Because of this part of the expression, that matches exactly with the big omega formula, right? So the constant a A times G of n is less than or equal to F of n, which is the big omega formula. And then similarly, you do the same thing, F is big O of G, because F of n is less than or equal to B times G of n. And you might say, well, is B the same thing as the constant C? The answer is, did the letter name matter? Nope. So we just say this is the big O of G formula, right? And that's really what we have to say here. And now there's a backwards direction of this proof. So then what we can do is just assume now instead that F is both big O, big O and big omega. Then there is a constant, maybe call it A, hint, hint. So that, right? So that this part is true here, right? And maybe I'll just cover this part up with a box. Maybe a white box. There we go. Right, so there is a constant A such that this, and there is a constant B such that, right, and now we pretend that we don't know this and we cover this side up, and then you say, aha, right? So we combine combine these inequalities. Okay, so I might give you a problem that's similar to this on the homework, and the reason why I'm going through this stuff in such detail is because my assumption is that you are not all math majors. So the issue is that when it comes to proof, the answer to the question, is this good enough, right? It depends. I mean, no one wants to admit this. Everyone wants to say, have you proved it to the standard of mathematics or whatever? But the actual secret is, it's have you proved it to the standard of the course, right? Of the course. So for instance, in Math 301, these proofs may be kind of laughed at a bit because they're not as precise. Definitely in Math 302, right? So if you take a proof class, some of these proofs may be kind of laughed at. This proof is actually probably good enough for a Math 301 proof, but I know that some of the proofs of my runtime stuff have not been precise enough for like a Math 301 proof. You would just end up, like the professor would just be like, they would write, huh? Or why is any of that? Right? And we're making a lot of assumptions and all that stuff. But in this class, as long as your argument makes sense, right? And uses the definitions and gets you to the result. We're not going to be mega precise about the nature of the proof. Like, is this sufficient proof for like a robot or a computer verified proof or whatever? Like, we're not thinking that. It basically, I'm going to read it and I'm going to say, here's my question that I'm going to ask. Here is the secret question. Not do I understand it. Not do I, the professor, understand what is being said here. Right? If I understand what's being said, that's good. But what I'm gonna ask is, do I think the student understands this proof? Right? That's what I'm gonna ask. Do I think that you understood what you're writing well enough to make the argument? Right? And so the thing is that a lot of people just throw down the formulas. They'll just throw down like these formulas and call it a day. They won't put any of the explanation of the sentence or anything like that. Remember, the proof, the whole goal of a proof should convince at least yourself, then me, then maybe the rest of the class, then a 301 professor, and then like a robot, right? So a proof should convince at least yourself. If it convinces you, then it's a good attempt at a proof. If it convinces me as well, then that means that you have proved something to the standard of the course, and I'm happy. And then maybe the rest of the class, like if you explain your proof to everybody, and then of course to a 301 professor who's going to be way more strict about the actual details here than we are going to be, and then like a robot computer verification algorithm, right? So that's like the highest level of proof in a sense. But you don't have to get here, right? So the good news is you don't have to get to this line of people, robots, right? So that's the idea of proofs here. And I think it's good that I just show you some examples of proofs, because you see, like, if you wrote basically this, right, on, without these boxes, obviously, you'd probably write something a little bit more clean, but if you wrote something like this on your test or on an assignment, I will accept it. It will be an acceptable proof. Okay, and so like the reason why I'm going through all these proofs and kind of the horrible, painful detail that we have today is just because I feel like there's always the question. And I remember when I was taking my Intro to Proof class, I actually took Math 301 here. When I took Math 301, I thought to myself, is this proof enough? Like, it proves it to me. I'm pretty convinced. It's pretty obvious that it's true. Will it prove it to the professor? The answer is, if you mimic most of what's here, you should be fine. If you try to get it to the same level of detail, you'll definitely be fine. If you just have the equations, if you just do that, it's not a proof because it doesn't explain anything, right? Like, if you just take these equations and combine them, it will convince me because I can read between the lines and I know what the proof is, but you have to pretend that you don't 100% know. Okay, so that's kind of, and I know that I spent a long time talking about this, but the good news is that we didn't have time to cover binary search trees today. So I might release a second lecture, because I know most people, about half of the people are watching these lectures late anyway. I might do a full binary search tree lecture tomorrow. And you don't have to watch it in real time. I'm just going to do it because I know that Comcast messed me up, and we lost, I think, 2 lectures, one because of the snow, and at least one because of Comcast. And so I owe you an additional week of lectures, so we have to catch up a little bit. So I'm going to do that. You don't have to watch it in real time. You can watch it later. But I think this is a good place to end it because I think we've gone over some stuff. And you see basically some of the more mathematical aspects of Big O. This may be the last time that you ever actually see this. Maybe you'll see it again in 441. But I just want you to have seen it once in your life, right? This is the have you seen it once in your life question, and now you can say, yes, I have. All right? So submit the homework by today or tomorrow. I mean, I think on Blackboard, try to get it in by tonight at midnight because that's when the due date is. I'm okay if you submit the... I added an extra day to the coding due date just because I want everybody to be able to get it in on GitHub. And I'm thinking that maybe I'll just switch all the submissions to GitHub. So if you submit your homework on GitHub, that's fine. If you submit the PDF on Blackboard, that's fine. Make sure you submit the code on GitHub, because not for the next homework, because the next homework is going to be primarily Big O and math, but the homework after that is going to be coding up stuff with regard to binary trees. And for that, I will try to make some pre-written tests that will, be good. So, submit your homeworks. I'm going to be around if you have any questions. I'll be available by text. I can even meet with people if you really have trouble with any of the problems. I tried to make homework 1 relatively deal-withable, so hopefully it is. Due tonight. The coding is due tomorrow because I'm a nice person. Okay, that's it. I'll let you go. Have a good rest of your day, Hopefully you'll learn something. Hopefully you feel like this was productive. Hopefully you feel like there wasn't too much math, even though this entire lecture was math. This may be the last math lecture for a long time, until we get to, I don't even know. Until we get to like binomial heaps and stuff. So we're gonna do like an entire month of like live coding after this. So this is like as much math as you're gonna see in the class. So we are, you know, f prime of t, or I guess math prime of t is equal to 0, and math double prime of t is what? Less than 0. So it's a maximum. Right? All right, I'll see you guys later. Now I have to find OBS to run the outro.